to the lecture now, 50th lecture. Last part 1, tomorrow will be the last lecture, and we started discussing op-amp offsets, then compensation and slew rate. These are the major imperfections of an op-amp which we would like to understand and discuss. Offset by definition is any phenomenon which makes the op-amp output non-zero if the signal applied is 0. Without any signal, if the op-amp output is non-zero, we say the op-amp shows offset. An offset can be either current or voltage, and this can be either at input or at output. At input we talk of offset input current and offset input voltage. At the output, since we do not measure the current, we only say voltage offset at the output. Offset voltage output, and the offset voltage output arises because there are offsets at the input. At the input, offset can be due to two reasons. One is current offset and the other is voltage offset. Now, as I said, the offset voltage output could arise due to, any offset arises due to mismatch of the two transistors at the input stage. Offset can also occur at succeeding stages, but it is the input stage offset which is the most important, and the reason is obvious, because the input offset voltage or current undergoes much larger amplification than any offset arising at an intermediate stage. Alright, most of the gain occurs in the first stage, then you make up for dynamic range, keeping the dynamic range within control, you make up for the rest of the gain, and therefore input offset is the most important, and that occurs at the first stage, which is a differential amplifier basically acting as a transconductance amplifier. That is, the output impedance of the first stage, the differential stage, is high, so basically it supplies current to the next stage. The input, as usual, is a voltage. Now, we had drawn a simple model of the op-amp taking account of the offsets, and we are considering DC offset. Offset arises basically because of mismatching of the two bias currents and the two VBEs, okay, the two base emitter voltages. And the simple model that we had shown was that if this voltage is VB2 and this voltage is VB1, and there is a difference between the two, VB2 minus VB1, if it is not equal to 0, then this appears as a signal between the two input terminals, and therefore it produces an output. And this voltage is called VI0. VI0 can be either positive or negative. There is no guarantee which terminal will have a higher voltage, therefore it could be positive or negative, but for uniformity's sake, let us say this voltage is VI0 with this polarity, plus and minus. I am intentionally confusing the terminals so that you can keep track of the sign of the offset voltage. Offset voltage VI0 could be either positive or could be negative. In addition, there are two bias currents. Let's call these bias currents as IB2 and IB1. VI0 is, let's say, VB2 minus VB1, and this is defined, the input offset voltage is defined as the voltage appearing between the two input terminals when the output is 0. This is the definition. Input offset voltage Vi0 is the difference between the two input terminals under the condition that V0 equal to 0. You understand what I mean? This is the general nomenclature that has been accepted by all manufacturers. They specify Vi0. Now obviously if there is a Vi0, there would be a V0, and to annul the offset voltage you shall have to apply a voltage in the opposite direction. Agreed? So what they do is, since you have to, they specify this by actual measurement. They don't make all these calculations and all that. Actual measurement, and actual measurement they can make. A voltage appears at the output. It is very difficult to measure the input voltage, because the input voltage will be a very small quantity of the order of a microvolt, for example, and therefore what they do is they apply a potential at the input such that the output is 0, and this potential is measured by an indirect means. Since it's a very small voltage, it is measured by an indirect means. Okay, so the input offset voltage is defined like this. Similarly, the offset current I0 is the difference between these two base currents. That is, and it is defined, it can also be positive or negative. Now let's define this as IB1 minus IB2. Okay, it can be positive or negative. IB2 may be greater, then this is negative. If IB1 is greater, then this is positive. II0, and this is also measured under the condition of V0 equal to 0. The definitions, the manufacturer specified input offset voltage, the input offset current under the condition of 0 output voltage. In other words, if there is an offset, there shall appear an output voltage. You annul that output voltage by applying an input current in the opposite direction. Okay, this is the general nomenclature, general specifications that are given in the case of an op-amp. Now obviously then our op-amp model, op-amp could be modeled in a slightly different manner by taking the difference between the offset voltage as appearing at one of the terminals. Okay, the difference between the two appears at one of the terminals like this, and then the input, that is between the between the inverting and the non-inverting, if the impedance, if the resistance is Ri, then this is the non-inverting terminal, and what we do is we bring out the two terminals and apply two bias currents as current generators. This is one of the models that is often used, IB2 and a bias current IB1. The difference between them is II0, the input offset voltage. If this is considered as Vi across the two terminals, due to the combined effect of IB2, IB1 and Vi0, we are not showing Vi0, VB2 and VB1 separately, we have combined them into one, and the model of the op-amp would be A Vi. If A is considered positive, then the polarity would be minus and plus, because Vi has been considered plus at the inverting terminal. You must keep track of this. The gain usually is specified as a positive quantity. If the voltage is of this polarity, obviously the output voltage will be of the other polarity, this, and you have an output resistance R0, and this is V0. This is the model of the op-amp, taking the input offsets into account. There are several definitions that are used in characterizing or specifying an op-amp, and I'll go through these terms, which you must be able to read and judge how good the op-amp is. Okay, one of the specifications is the input bias current. Obviously this doesn't mean anything because there are two inputs and the bias currents IB1 and IB2, you have to specify two, but what the manufacturers usually specify is the average value of the two, IB1 plus IB2 divided by 2. okay, when again under the condition when V0 is equal to 0. All right. Input offset current. As I said, this is IIO, input offset, and it is defined as IB1 minus IB2, again when V0 is equal to 0. There is also defined input offset current drift. This is also specified. This drift is with regard to temperatures. That is, this is defined as delta IIO delta capital T. If temperature changes, how does the input offset current change? Okay. This changes because beta changes, VBE changes, and therefore the offset will also change. Oh, we don't have a specific, it simply say delta II0 by delta T.
And is this under particular conditions, sir?
It is under no particular condition, because this does not depend on the load. Load is far away from it is the absolute value. Delta, and you see II0 is defined with V0 equal to 0. So delta II0 delta T obviously is with respect to the same condition. And then input offset voltage. As I said, this is denoted by VI0, and this is VB2 minus VB1 for unknown reasons. They take V2 minus V1 when V0 equal to 0. And once again, you can also define an input offset voltage drift as delta VIO delta T. This is also specified by the manufacturers. Normally, naturally, the smaller the value, the better is the op amp. Okay.
So II0 and VI0 both be defined for some particular temperature.
Room temperature. Yes. Room temperature is taken as 25 degrees centigrade. No, it's taken as 300 degrees K, which means 23 degrees centigrade. 27, I beg your pardon, 27 instead of 25. Okay, room temperature is taken as 27. That is the reference with respect to which all other temperatures are specified. Okay, now next is output voltage offset. This is this is V0. Instead, I mean, if you want to specify offset, then you call it V0S, VOS. That is output offset. I can't use a VO. We can use a VOO if you so desire. Okay, that is also all right. But this is defined under the condition that the plus terminal, the non-inverting terminal, and the inverting terminal of the op amp are connected together. Okay, that is a common mode voltage is applied. No common mode voltage is applied. They are simply connected together. So whatever voltage appears at the input shall be a common mode voltage. Then you measure the output. This is the definition of the voltage offset at the output. There are a few other terms which it is good to know at this stage, because that will complete the characterization or specification of an op amp. The first is input common mode range.
So why does the output voltage offset need to be specific?
Why does the output? You see, even if there is no signal and the two inputs are connected together, if there appears an output, obviously that is an output voltage offset. But this offset arises because of what? Not input offset voltage, because the two inputs are connected together. It is due to the difference in the bias currents or current offset. Okay, that is a measure. Input common mode range is the common mode input signal range which can be applied without the differential amplifier becoming non-linear. That is, if the differential amplifier, if the op amp characteristics, I shouldn't say differential amplifier, if the op amp characteristics this is the input, this is the common mode signal range which can be applied to the op amp without the output going into the nonlinear region. It's a very qualitative thing, but it gives you an idea as to what common mode signal you can apply. All right. Then similarly, input differential range. Differential range is the maximum differential signal that can be applied to the OA operational amplifier input terminals. Again, without the output going into the nonlinear region. And you know that for a differential amplifier, it's approximately, what is the range? 4 VT, 100 millivolts, approximately 100 millivolts. Okay, so this is defined for the total op amp, input differential range. Then a quantity which is also somewhat non-analytical, a qualitative, output voltage range. You know that the output voltage, what is the maximum output voltage that you can get out of a differential amplifier? If VCC and VE are equal, then the maximum is 2 VCC, plus VCC and minus VCC, maximum range, okay, 2 VCC. Often you cannot go up to VCC, you must stop a few volts before VCC. This is because either the amplifier goes into saturation, on both sides it goes into saturation. So you must avoid that nonlinear region. So a few volts, maybe if the supply is plus minus 15, plus minus 12 is usually specified by the manufacturers. This is the output voltage range. Your output voltage must not exceed plus minus 12. Then you will get into the nonlinear region. Okay. Then a quantity which you have not come across so far is full power bandwidth. Full power bandwidth. This is very much related to output voltage range. Full power bandwidth is the maximum frequency of a sinusoid. Maximum frequency of a sinusoid for which the output can reach the limit of output voltage range. You understand this? It is the maximum frequency of a sinusoid for which the output can reach its limiting values. Now, why is there a maximum frequency? Because every op amp has a bandwidth. Whatever connection it is, there is a bandwidth. Okay, it cannot go beyond that. If it goes beyond that, obviously the output shall decrease. If the frequency increases beyond the full power bandwidth, then you cannot reach plus minus 12. That's what it says. Okay, so this frequency shall be specified. It is a bandwidth specified in hertz. So many hertz. Then there is a quantity called PSRR. It is the power supply rejection ratio, and it is defined as, there are two power supplies basically in op amp, plus and minus. If one of them changes by a small amount, let's say from 15 to 15.001, it is all stabilized with Zener's and voltage regulators, but even then, suppose it changes due to a temperature change or some other change, how much does the input offset voltage changes? So it is the ratio of change in VIO divided by change in one of the supplies, one supply, keeping the other fixed. Okay, is this point clear? One at a time, one supply changes, how much is the input offset? Okay, and this ratio is PSRR. PSRR normally is to be very, very high, very, very high, and this is why the voltage regulator chips are so important. No op amp can be driven without a stabilized power supply. Finally, the quantity that is slightly mysterious, but we shall decode this, is called the slew rate. It turns out one of the manifestations of slew rate, we'll approach it from different angles, but slew rate, alright, first the definition, it is the rate of change of the output voltage dV0 dt maximum rate of change of the output voltage at large voltage inputs, okay, under large signal condition, we shall see why this arises, but the external manifestation is that if you apply a step, if you apply unit step, okay, what do you expect? After all, the op-amp can be modeled by a single pole, as we shall see. It has to be a single pole, dominant pole model. If it is a single pole, then it behaves as a low pass circuit. In a low pass circuit, if you apply a unit step, low pass circuit, simplest example is series R, shunt C. If you apply unit step, the output voltage should rise exponentially. It's a peculiar phenomenon in an op-amp, large gain op-amps like this, integrated circuits, that the rise is linear. At sufficiently large signals, the rise is not exponential. It is linear. The maximum linear rate of rise that you can achieve is called the slew rate. We shall go into further details of this and see why this arises and what is its value. But first, let's clarify some of the concepts of offset by taking some simple examples. Okay. First, let's say we have an inverting amplifier with two resistances R and R prime. R prime is 1 meg and R is 100k. So the gain would be how much? 10. Okay. It's a gain 10 amplifier. And this is grounded. This is how usually we draw the op-amp, correct? It is given that Vi0 is equal to 0. Please follow these simple calculations carefully. There are some simplifying assumptions and very simple calculations are required. Then the concept of offset gradually seeps in. Vi0 is equal to 0 and the input voltage offset is 0, but the base currents, the two input currents are equal, so there is no input offset either. There is no input offset current. IB1 equal to IB2 equal to IB, the manufacturer's definition, the average value of the two is 100 nanoampere. Okay. Now you are required to find out V0, output voltage. All offsets are measured with the inputs connected to ground, no signal, under no signal condition. No signal condition means that we have to ground this. What is V0? The question is, it is given, this is an inverting amplifier of gain 10. It is given that input offset voltage is 0. The two bias currents are also equal. There is no input offset current either. But this current is 100 nanoampere into both the bases. Will a voltage appear or not? If so, what is this voltage? Okay. The solution is extremely simple. You see, because of virtual ground, this point is virtually grounded. If this is grounded, pardon me?
Why did you ground the other terminal?
Oh, offset voltages and currents are always measured with no signal. No signal means not open. It must be connected to ground.
So how do you measure the input offset voltage by if you are grounding both the input terminals you are grounding?
No, if I put this to ground, I will measure between these 2 points. You see, if both the inputs are grounded, then you have an objection, because both inputs are connected together. But if it is connected to ground through a resistance, the input offset voltage shall still appear.
So assumption of virtual ground will not be valid here?
Will not be valid, but we will assume in calculations that it is valid. All that it requires is that the gain should be large. That's all it requires. So we assume that the gain is of the order of 10 to the 6, so that this potential is virtually 0. If it is 0, then obviously no current flows through capital R. Agree? If it is 0 and 0 here, no current flows, and therefore the bias current, which is IB2, must come like this. Okay? IB2. And therefore V0 is simply equal to IB2 multiplied by R prime. Is the point clear? If this potential is 0, no current in R, and therefore the current must come like this. And therefore V0 would be simply IB2 multiplied by R prime, which is 100 times 10 to the minus 9 multiplied by 10 to the 6 volt, and this is equal to 100 millivolt. Now you see the phenomenon, you see the peculiarity that even if there is no input offset voltage, even if there is no input offset current, the base currents are exactly identical, still an output offset voltage appears. That appears, can you guess the reason? The reason is that the two inputs are not under identical conditions. One of the inputs is connected to ground through a 100K, this one is connected directly to ground. The remedy for this, that is no input offset voltage or current, if you want no output offset voltage, the remedy is that you connect a resistance here. Let us see what happens. This is part B of this exercise. Suppose we connect a resistance. We call this resistance as R1, this is R, this is R prime, and this is V0. Okay, we want to choose R1 such that V0 is 0 when Vi0 equal to 0, IB1 equals to IB2. Well, it turns out that this resistance can take care of the condition even if IB1 is not equal to IB2. Let us see how. Since V0 is 0, this is our assumption, we want to make V0 equal to 0, therefore R and R prime are virtually in parallel. Is that clear? Therefore the current IB1, was it IB2 or IB1? IB2. Let this current be IB1. Since V0 is 0, R and R prime are in parallel, therefore V minus, that is the voltage at this point, would be equal to minus IB2 multiplied by R parallel R prime. Agreed? This is the voltage at the inverting terminal, whereas the voltage at the non-inverting terminal is minus IB1 multiplied by R1, and therefore the condition for V0 equal to 0 should be that no voltage should appear between these 2 points, which means that V0 equal to 0 implies that IB1 R1 equal to IB2 R parallel R prime. Even if the two bias currents are not equal, that is, even if there is an input offset current, you can compensate for this by using another resistance R1. Normally the voltage here is still 0. Okay, if there is no bias current, if the bias current is 0, then it doesn't matter, it is virtually grounded. But if there is a bias current and there is an offset input current, everything can be taken care of by introducing another resistance. And therefore wherever you see in the textbook or in an experiment manual or manufacturer specification that the inverting amplifier is like this, it is implied, actually they can't show you what resistance it is. It is implied that this is connected to ground through a resistance which is approximately the parallel of these two. this will drastically reduce the offset voltage and current. Okay. In this particular case, if IB1 is equal to IB2, then R1 that is required would be 0.1 meg parallel 1 meg, which is equal to 90.9 K. This is required for offset balancing.
Is the gain affected?
Pardon me?
Is the gain affected by the resistance?
Is the gain affected? No, the gain is not affected. The gain is not affected because there is, as far as AC is concerned, this is zero potential. Yes.
What about the problems in the fabrication of this such a high resistance value?
It is not fabricated. It is connected from outside. When you use the op amp, you have to connect this from outside because you connect R and R prime also from outside, depending on what gain you want. These are not internal to the op amp. These have to be added. Now, using this result of the previous part, that is, you have, what was this value? 100K R, and R prime was equal to 1 meg, negative, positive. This is 90.9 K. Now suppose in this op amp there is an offset current. IB1 minus IB2 is 20 nanoampere. We connected this resistance assuming that IB1 was equal to IB2. Okay, we assume that IB1 is equal to IB2. Now if this is not true, then how do we, if this is so, what is the output voltage under this condition? Okay. Now see the how do I calculate this? We argue like this. IB2, look at this argument. IB2 is IB1 minus 20 nanoampere. If, well, this is IIO, okay, input offset current, therefore it is IB1 minus IIO. If IIO was 0, then there would have been no output voltage. Agreed? Because if IB1 is equal to IB2, we have already compensated for this, and therefore the effect of IIO can be modeled by assuming IB1 equal to IB2 equal to 0, but there is a perturbation on IB2 of a current IIO. Is the point clear? And this of course has to be grounded. The effect of IIO can be modeled by zero current here, but a small current IIO here. Why in the other direction? Because it is IB2 minus IIO, IB1 minus IIO. Alright? Now, since there is no current here, this potential is 0. Agreed? This potential is 0. So, what about this potential? Also 0. So, no current flows through R. This current therefore must flow like this. Therefore, V0 would be equal to minus IIO times R prime, which in this case comes out as minus 20 millivolt. Alright? These are the ways things people calculate, make compensation and so on. Is the point clear? Now let's complicate this matter further. Suppose, yes? Which current? Oh, you see, if we take IB2 here totally and IB1 here, it is only the differential current that is causing an output voltage. So we could as well assume that IB2 is equal to IB1, that is the two currents are equal. This is the perturbation. We only take care of the perturbation because the common current causes a V0 equal to 0. The circuit is linear and therefore superposition applies. Yeah.
So the presence of a virtual ground at the negative terminal,
Yeah.
that will only happen if the positive terminal is grounded.
That's right. But it is now, it is not grounded. It is connected to a 90.9K, but equivalent current through this is 0. And therefore this potential is 0. Therefore this potential is 0. Okay? This is a simple kind of argument than what that one uses.
So
Now,
if the currents in the two terminals, the inverting and the non-inverting terminals is not the same,
yeah.
then is the idea of virtual ground actually valid or not?
Is the idea of virtual, now there will be no virtual ground. If there are two currents here which are unequal, virtual ground can be restored by taking the difference current here. Okay? So that this potential is made 0. Now, let us complicate this matter further. Next part. Suppose IIO equal to 0, no input current offset, but there is a VIO which is 5 millivolt. Okay? So, you are required to find out what is VO under this condition. For the same circuit, that is, we have an R prime, inverting, non-inverting, and this is R1. For the same circuit, there is no no input offset current. VIO is 5 volt. 5 millivolt. Okay. Now, if that is so, since there is no input current offset, well, this potential is still 0, and this potential is 5 millivolt. Therefore, the current through R is VIO divided by R. The current through R is VIO divided by R. And where should this current go from? No input offset, so both the currents can be assumed to be 0, so it must come like this. Right? And you can easily show that VO would be equal to VIO 1 plus R1 by R, R prime by R. Very easy to show. V0 is this I into R1 plus R. Okay? And VIO is I into R. And therefore, this is the ratio. That is the gain 1 plus R prime by R. In other words, under this condition, V0 would be equal to 5 millivolt. Then 1 plus the gain is 10. And this offset, we have not assumed a polarity, so it could be either positive or negative. So we add plus minus so many millivolt, which is obviously 55 millivolt. What was the value for offset current of 20 nanoamperes? What was the value of the voltage? 20 millivolts. So this is comparable. Alright. Suppose both are present now. Suppose IIO is equal to 20 nanoamperes and VIO is equal to 5 milliampere. Then under this condition, what would be V0? V0 would be the superposition of the two. Minus 20 millivolt, okay, plus minus 55 millivolt, right? Or any combination of them. This could also be plus minus. But I want you to notice one thing, that V0, if I write the equation, minus IIO R prime plus VIO 1 plus R prime by R. Please follow carefully. This is how we calculate it, by superposition. Now you notice that as far as gain is concerned, all that matters is this ratio, R prime by R. Isn't that right? Changing R prime and R, that is scaling the resistances. Instead of 1 meg, let's say we make it 0.5 meg. Then instead of 100K, we have to make it 50K. That does not change the offset output due to input offset voltage, but it definitely changes due to the current. Isn't that right? And therefore, to reduce the current offset, the lower the value of the resistance, the better. Is the point clear? scaling the resistance. You see, this is proportional to R prime. So if R prime is reduced by a factor of 2, the contribution to the output offset voltage to the input offset current reduces by the factor 2. But it doesn't change in the case of the offset voltage.
So, but it may not be always true if the current offset part
Yeah.
is going against the voltage offset part.
Okay,
Then you
the
might-
magnitude.
Yeah.
The magnitude changes, it reduces. So the worst case would be 55 and 20 minus 75, okay, or plus 75. But you see the contribution due to II0 decreases if the resistances are scaled down. This is the important point. Whereas the contribution due to the input offset voltage does not change because it depends on the ratio. Okay. Now, if there is an offset of, let's take this particular case, 20 nanoampere and 5 millivolt, and your signal itself is, let's say, a pickup from a sensor, maybe a vibration sensor, which picks up signals of the order of 1 millivolt. Oh, then your offset is going to offset everything. Isn't that right?
But it will be just shifted.
It will be superimposed on the output voltage of 75 millivolt, okay, and you will be nowhere. The signal itself would be shifted, and there is a DC level, and therefore further processing will become a problem. All right. So what one does is, if there is an offset, and it's a very sophisticated application where the signal level that you pick up is very, very small, you have to balance the offset, and this balancing is done by connecting a small voltage source to one of the terminals. All right, and let me show you the circuit. If you are interested in a non-inverting amplifier, then the balancing circuit is applied to the if you are interested in an inverting amplifier, then the voltage, the additional DC voltage is connected to the non-inverting terminal. For example, you have an inverting amplifier like this, R prime and R. To this point is attached a small voltage source, and this voltage is made adjustable so that you can exactly offset the effect of offset. All right, so that you can make V0 equal to 0 under no signal condition, and this is done like this. You connect a resistance R2 here. I'll show you the typical values later. Another resistance R3, and then a potentiometer, the ends of which are connected to the VCC, plus VCC and minus VCC. Suppose these are plus VCC and minus VCC. The potentiometer comes here. Okay. So the voltage that you can apply here shall range from plus VCC R2 by R2 plus R3, this is the maximum that you can get, to what is the minimum that you can get, minus VCC multiplied by R2 by R2 plus R3. And any offset, whether it is due to current or due to voltage, all you need is, I don't care what happens here, all I need is, when there is no signal, when this terminal is grounded, I must have a 0 voltage here, right? So you adjust this and you make it equal to 0. This could be a positive voltage or could be a negative voltage depending on the polarity of IIO and VIO. All right. The typical values are, this is a 50K port. Please remember that these are all to be connected at outside. Okay. This potentiometer typically is 50K, R3 typically is 100K, and R2 typically is 100 ohm. Obviously the resistance from here to ground cannot be maintained at R parallel R prime. That was required for compensation of offset. Even if the two bias currents were equal, there would appear a offset voltage, and we required that. Now, since you are applying an external voltage, we don't care. We will make V0 equal to 0 by what is called a brute force technique. Okay, we will apply a voltage, and you see, this is required in very sophisticated applications, and in any measurement application, for example, the first thing you have to do is to make an initial adjustment. There would be an adjustment on the instrument which said offset adjustment. You will have to change this, connect the input terminal to ground, you will have to change the potentiometer till the output voltage is 0. Okay, and then you apply your measurement technique. If the application is that of a non-inverting amplifier, obviously all this arrangement will have to be made, will have to be connected to the end of R. Is the point clear? And the input is applied at the non-inverting terminal. Agree? We will continue this discussion tomorrow.